start on the first of. Oh, right, sorry about that, guys. Three circuit analysis techniques for DC circuits. We'll also be looking at one or two of them possibly with AC circuits as well. Okay, so we're going to start with today is the concept of an ideal voltage source and an ideal current source. If we have a circuit as shown there with a voltage source of 10 volts, feeding a load resistor RL, we get a load voltage across there that would be equivalent to the 10 volts. So the ideal voltage source has zero internal resistance and will provide you with the same terminal voltage here, regardless of how much current flows, regardless of whether we put a small value resistor on or a large one. It will always give you the same terminal voltage of 10 volts if it was ideal. Okay, so meaning that the voltage of the load is always equal to the voltage of the source, regardless of whether the value of that load. In reality, no voltage source can achieve this. And in a way, you've seen that in your practical, particularly with the filter. Remember, as the load changes, as you changed frequency and the impedance of your filter changed, so it affected the voltage of the input, the source. Okay? So a real voltage source cannot provide the same terminal voltage regardless of the current that you draw from it. So what we need is a way of representing a real voltage source. And we do that, and you should remember this from your attenuator practical, is that we simulate the internal impedance of a source by having an ideal voltage source in series with its internal resistance or impedance. We can use resistance when we're talking just about DC. With any AC involvement, we need to say impedance. Okay, so a real voltage source can be represented like this. A source of, say, 10 volts, ideal. So that voltage source will always give you 10 volts. Like the voltage source in multisim, will not vary according to load. But we simulate that variation through the load by having this series internal resistance. With your practical, your source, the signal generator, had that internal impedance inside it, a switchable 50 ohm or 600 ohm. So that was that resistor there is representing that. Okay. So when this circuit is open circuit like it is now, we would measure across there 10 volts because there's no current flowing. Therefore, the volt drop across the internal resistance is 0 volts. If this is 10, remembering back to first year science, clockwise arrows. Hang on. Oh, Michael, you've done that wrong, haven't you? Current's flowing that way. So, current's flowing that way. That's a clockwise arrow. This one should be that way. Clockwise arrow. Anti-clockwise arrow add up to each other. Kirchhoff's law. Yeah? Okay. So at open circuit, we'd have the 10 volts terminal voltage of the ideal voltage source. However, when we draw some current, i.e. we connect a load, then we would get a voltage drop as soon as current flows. If this had a value of an ohm, if we had 1 amp flowing, volt drop across there would change to 1 volt, and this would drop to 9 volts. And as you draw more current from the circuit, that voltage would go up, this one would go down. And think about what happens if you turn the lights on your car, and or the radio, but the lights in particular, and then try to start it. The high current being drawn from the battery when you start and will make the lights go dim. That's because that's dropping the terminal voltage of the battery, because you're drawing so much current from it to start the engine. Right? So, an example calculations for you have a go at. If the open circuit voltage of the battery is 12 volts, i.e. this ideal source is 12 volts, okay, and its internal resistance is 0.5 ohms. Find the terminal voltage of the battery when currents of 2 amp, 20 amp, and 80 amp are drawn from it. Okay. 5 minutes. How have you done it? When I equals 2 amps. Yeah. So VRS is equal to the volt drop across the internal resistance is 1 volt, therefore terminal voltage equals 12, wasn't it? 12 minus 1 equals 11 volts. Yep. No, that wasn't what I wanted. There it is. So when I equals 20 amps, VRS equals what? Ten volts. All pretty quiet today, aren't you? Therefore, V terminal is equal to 12 minus 10 equals 2 volts. What about the 80 amps? Not able to achieve that, is it? No? Okay. Well, yeah, you would hope it would be fused, so it would blow a fuse before it got to that situation. But it's like the reason why it's not really a good idea to check that your battery's got some kind of charge in it by putting a spanner across the 2 terminals or something like that, because you're effectively pushing tons of current through that internal resistance, which is not a resistor. That's the plates and the acid in the battery. If you had that on there for any length of time, you'll boil that acid and possibly cause an explosion. Not really a very good idea. Okay. Well, if that's what you're trying to achieve, then you'll achieve it. But you know, you might also achieve a face with no features. All right. So there are always limits, of course, to what that kind of idea of simulating that internal resistance can do. That's why I put the 80 amps on there. It's not achievable. All right. So the most important thing to get from those pieces so far, what we've done so far, right, is this. Ideal voltage source has 0 internal resistance. You're going to need to remember that fact for the other techniques that we're going to use. So an ideal voltage source has no internal resistance at all. All right? So make sure you remember that fact. Moving on. Ideal current source. Okay? Now, if that symbol there you've never seen before, but it's the symbol for a current source, a constant current source. Always going to deliver 2 amps. Okay? Like the ideal voltage source, it's got a internal resistance such that it is infinite. No current is lost in the ideal current source. It all goes through the load, okay? And it will always deliver 2 amps regardless of what that load is. Again, like the voltage source ideal, it cannot be achieved. Right, as we change load, we must get a change in situation, and therefore we simulate the actual internal resistance of a real current source by a parallel resistance. This so-called perfect current source would always deliver the same current and have its terminal voltage Vt determined by what the load resistor was. So in the voltage source circuit, the current was determined by what load you connected and what the internal resistance was. In the ideal current source, the terminal voltage is determined by the load. Yep. One thing to note is you can have a power supply designed to, between certain limits, hold the voltage at a given voltage and allow the current to vary, or you can hold the current a particular current and let the voltage vary, but you cannot control both at the same time. They're mutually exclusive. If you want a constant current, you've got to allow the voltage to go up and down. If you want a constant voltage, you've got to allow the current to go up and down. Okay? Now, if we want to represent a real current source, we do that by the ideal current source and its infinite internal resistance, i.e. open circuit, in series with its actual internal resistance. There's our terminal voltage, and there's our load. So, what happens is, if the load is really high, bigger than RS, more current will flow through there, and less will go through the load. If the load is smaller than RS, you'll get less current through RS than you get through the load. So that's how a real current source would be represented in diagrammatic form. When the terminals are open circuit, so if we disconnect this resistor, all of that 2 amps will flow through RS. It should be noted that this is a representation of a current source that represents how a real one would operate in reality. It simulates it. It is a representation and not a real circuit. The voltage one is a little less conceptual than this, but the current one is sometimes a little bit more difficult to get your head round, because to cause a current to flow you need a voltage source. But it's just around, are we interested in keeping the current constant, or are we interested in trying to keep the voltage constant? All right? So, everybody reasonably happy with that so far? And again, the thing to remember here for the other techniques is internal current source has infinite internal resistance. An ideal one does. Okay? And you represent an actual one by an ideal current source in parallel with its internal impedance. So an ideal current source of 4 amps has an internal resistance 60 ohms. Find the load current at the terminal voltage when the load resistor is A 20 ohms and B 150 ohms. Rule of thumb check. Total for 2 parallel resistors is always less than either of the individuals, so that's a good indication. 20 is our lowest one, 15 is less than that. Next thing to do, VT, calculate voltage, Ohm's law. I times RT, 4 times 15 equals 60 volts. Therefore, IL current is terminal voltage divided by RL, 60 over 20 3 amps. So, with a load of 20 ohms, 3 amps of our source current, ideal source current, is going through RL, and 1 amp of it is being lost due to the internal impedance within the. So we got one in this situation. We got 1 amp going down there, and 3 amps flowing in the load. Now do the calculations for the load resistor being 150 ohms. Right, so what we got for RT in that condition then? With 150 ohm RT. .9 ohms. Hang on, put that in the wrong place. So VT, terminal voltage, .43 then. Well, this round up was 100 watt. $172 over 150 is 1 point. What was it? 1.15 or. Yeah, so in the case of the bigger, the resistance being bigger than the internal resistance, we've got more current lost inside the source than we have going through the load. Yep. Okay. So that's the basis of ideal voltage and current sources and how we would represent a real one, by including either a series resistor with the ideal voltage source or a parallel resistor for an ideal current source. Everybody happy with that? Right then. Put that in there. really want that. We'll leave that one for now. You can have a go at that one on your own. Right, we're going to go on to this now. Network theorems. Okay, there are a number of network theorems electrical people use, engineers use to analyze circuits and help to simplify circuits and so on. Okay, these include superposition theorem, which we're going to do the rest of today's session. Perhaps pick up on it a little bit next week, see where we get to. Thevenin's theorem, Norton's theorem, and maximum power transfer, which we've already come across a little bit because we talked about matching your attenuator, making your attenuator match, so you get the impedance of the source and the load matched and get maximum power transfer. Okay. What we'll do is consider how these are used for DC circuit initially. Okay, so it keeps it reasonably easy because we've not got any complex numbers involved, and then we'll have a look at one or two of them for AC circuits where things get a little bit more complex. So, the superposition theorem, and I'll put a worded description. It does sound a little bit more complicated than it actually is, okay? But it states that in any network containing more than one source, so that could be 2 voltage sources, 2 current sources, or a mixture, 3 voltage sources, so on. In a network containing more than one source, the current in or potential difference across any branch in the network can be found by considering each of those sources separately and adding their effects. So we're not going to, and you'll not be given in the exam a circuit with any more than 2 sources, because you're not achieving, in learning sense, any more by doing 3 or 4 sources than you are by doing 2. You just got more work to do and it takes longer. Okay, so you're only ever going to get 2 sources. When the contribution of one source is being calculated, and this is why I've told you the important bits in the previous work, other sources in the network are replaced by a resistance equal to that ideal internal resistance. So what we do is, if we're considering voltage source number 1, and we've got voltage source number 2 as well, what that paragraph says is we take out voltage source number 2 and replace it with its ideal internal resistance. Nothing. Short circuit. So we take out the second voltage source, short circuit. And then we do the same, taking out voltage source 1, do calculations for voltage source 2, add all the results together in each branch to get the overall currents and voltages. This may sound a little bit complicated, but as long as you apply a methodical approach and label everything carefully, it is relatively simple and best illustrated through an example. So what we're going to do is use the superposition theorem to calculate the currents in the circuit above, and hence find the power dissipated in a 30 ohm resistor. We'll probably also do, I think I use the same circuit with Norton's theorem as well, so you can, Norton's and Thevenin's as well, so you can see that the results for a particular area come out the same. But what superposition will allow you to do is find out all the currents and all the voltages in the circuit. What Norton's and Thevenin's do is simplify the circuit so that you can check how the circuit would behave with different loads, and more about that next week. Alright, so here we're going to use superposition to calculate the currents in the circuit and find the power dissipated in this middle resistor here. Okay, all happy with that? So the first thing we do is we remove the second voltage source, V2, and replace it with a short circuit. So when I do this by hand, I like to do this. That's where the voltage source was, and I'm going to take it out and put a piece of wire across it and make it 0 resistance. Yeah. Then what we do is, and I'm going to call this, well, I already called it circuit A. So all my values in this circuit are going to have an A suffix after them, so we know where we are. It's all about labeling things properly. Next thing to do is add current arrows as per normal conventions for each part of the circuit. So this arrow here signifies that that's the positive side of that battery or cell. Which way would I put current in this R1 leg? Which direction? Which way is current going to flow by convention from that battery? Yeah, clockwise, away from. So I'm going to put a nice arrow on there, make sure you get the direction right, and call that I1A. And where would we put current in the middle leg through R3? Down, yeah. I3A, and in this leg, that way. Have you got my I3A? So calculate the 3 currents in circuit A. Where are we going to start with that? Where are you going to start? You can calculate I1A how? Think about it a bit more clearly than that. This current that's flowing here, when it gets here, some of it's going to go down there and some of it's going down there. So why haven't you included R2 in your resistance calculation for that current? All the current that leaves here has got to go round and come back here. It can go through those two, but eventually has to come through R1 and back to there. So what kind of circuit have we got? We've got 2 parallel resistors in series with a third one. Yeah? Just because they're drawn, this one's down here and not up there, it doesn't mean you haven't got that. It's just 2 parallels first, and then a series. So RT is R1 plus the other 2 in parallel. Yep. 6 plus 5 times 30 over 35 equals, I'm sure someone will push those buttons for us. Yep, so we got our first current, I1A. Yeah, it's travelling upwards in the R1 leg, and it is 1.17 amps. I'm going to go 2 forward now. I1A, 1.17 amps. Yep. Put these on here now. I3A equals and I2A equals. We're eventually going to have all our currents on that diagram, and then use that to find out what the overall currents are. All right? So that's now. How can we find I2A and I3A? You know, we've got 1.17 amps flowing here. How can we find? There are 2 or 3 ways you could go about it. What way do you fancy? Nobody? Is the 12 volts across just that resistor? Yeah, you've got a current flowing in there, so we got VR1 here. VR3 and VR2 are going to be the same. They're going to connect to the same place. Back to this networks that we done in science. So, how can we find, if we can find VR3 or VR2, they're essentially the same because they're connected to the same place across one resistor. Yeah, everybody understand that? So how can what are the ways I could find one of those 2 voltages to get me in this, or that voltage? Yeah, we could find VR1 and then do what with it, Alex? Take it off the 12 volts, yeah, because by Kirchhoff's law, if we take this loop here, remember, there's a clockwise arrow and 2 anti-clockwise arrows. Those 2 have got to add up to that one. So if we find that voltage, we know the current going through that resistor. So if we find that voltage, we can take it off the 12, and we'll have what's left there by Kirchhoff's law. So if we go VR1 is equal to I1A times R1, 1.17 times 6. .02 volts. Therefore, by Kirchhoff's voltage law, V2 equals V3 equals V1 minus VR2 equals 12 minus 7.02. Was 12 volts, wasn't it? Yeah, 12 volts minus 7.02 volts is 2.98. No, 5.0, 4.98. Yeah. Therefore, I2A is equal to V2 over R2. That's the 4.98 divided by 5 ohms equals, and I3A There's V3 over R3, 4.98 over 30 equals 0.900 and what? I'm going to keep them to amps if you don't mind, but I understand why you've done what you've done. And I3A, and add those two together, what do we get? What? Yeah, more or less, allowing for random errors and such like. Yep. These two currents should add up to that one by Kirchhoff's current law. Yeah? So you've got the values. Tell me, I3A was 0.166 and I2A yep. So that's circuit A. Now what you need to do is go through the same process for circuit B. Label them the currents I1B, I3B and I2B. Okay. You've got R2 in series with R1 and R3 in parallel for total resistance. Okay. Right, how are we doing? Value for the total resistance of the circuit. Sorry? 10 ohms? You don't like that, yeah? Therefore, I2B is how many volts was it? 10? 1 amp, yeah? Yep. VR2B don't know anyone in Manchester, go away. So the voltage across this resistor comes out at 5 volts. Therefore, VR1 and VR3 is equal to 10 minus 5 equals 5 volts. Yep. Therefore, I1B 5 over 6. Someone push that numbers, please. 0.166 amps. I think that's probably 7 rounded, isn't it? 0. What? And I3B 5 over 30, 0.167. And those two should add up to an amp, and I believe they do. Yep. So, to finish off and find the actual currents, all we got to do is put those currents on here. Now, I1B was a current going downwards of 0.833. Am I right? Yeah. I3B was a current going downwards, 0.166. No, hang on. This was 867, wasn't it? 833. And this was 67, yeah? And this one was upwards, I2B equals 1 amp. To calculate overall currents, I1, I2 and I3, you do this. If two currents in the same direction, you add them together. Yep. If two currents opposite in direction, subtract smallest from largest with resultant current being in direction of the largest one. Okay, so if we look at these, for I3, 2 arrows are operating in the same direction, so I3 is equal to 0.166 plus 0.167. Yeah, and that they're both going downwards, so the result is downwards through that middle leg. Okay. For I2, the blue current is bigger than the green one, therefore we take 0.966 away from 1 amp. Whatever's left will be in the direction of the blue arrow. Okay, and here we would take the blue value of 0.833 away from 0.17 because that's bigger, so the direction there would be in the direction of I1A. Okay.